Hi, my name is Jacob Horton. With me are Jeff Williams and Ryan Elliott, and we're presenting our demo on eddy currents for MAE 535. Michael Faraday observed in 1831 that when it's exposed to a time-variant magnetic field, an electromotive force, or EMF, is generated in a stationary coil. This observation is characterized by Faraday's first law of induction, which states that the EMF generated equals minus the rate of change of magnetic flux with respect to time. So although this was first observed for a moving magnetic field, the relationship holds for a conductor moving through a stationary magnetic field, which is in our case represented by a pendulum. The generated EMF induces currents known as eddy currents in the conductor, and by Lenz's law, the direction of the currents is such that the magnetic field created by them opposes the field that produced them. And this is noted by the minus sign in Faraday's law. Additionally, the magnitude of the EMF is proportional to the velocity of the pendulum moving through the magnetic field. So next we can use Ohm's law to obtain the magnitude of the current induced in the conductor. This is dependent upon the conductivity of the conductor, so it will vary between materials. And finally, using Lorentz force law, the magnitude and direction of the forces found in the regions where the pendulum is entering and leaving the magnetic field can be found. And that's noted in the graphic.
So as Jacob mentioned, we opted to demonstrate this phenomenon with a pendulum with magnetic braking. So to the left, you can see our cardboard base of our pendulum. Our rotational arm was an aluminum ruler fixed to the base via an eye bolt. At the bottom of the ruler, you could fix four different types of sheet metal. You could fix a flat aluminum piece of sheet metal, a piece of aluminum sheet metal with teeth cut into it, a flat piece of copper sheet metal, and then a piece of copper sheet metal with teeth cut into it. That was made to swing through two magnet housing brackets pictured to the right, and three N52 magnets were fixed to either magnet housing bracket to generate our magnetic field. So our data collection method, we put each piece of sheet metal through the test 10 times and recorded the average number of oscillations and the average distance of each oscillation for each piece of sheet metal. So taking a glance at our results, and as you'll see in the data and the videos we are about to show, the copper will experience more damping than the aluminum, and the cut pieces of metal experience less damping than the flat pieces of metal that were uncut. So here's our solid piece of copper versus the cut piece of copper.
And the reduced damping of the cut sheets is because the discontinuity at the bottom of the cut sheets, the induced currents are smaller in magnitude and provide very little braking force.
And this can also be observed in the flat piece of aluminum versus the cut piece of aluminum, lesser so than in the copper, however.
When comparing the solid copper and the solid aluminum sheets, it can be observed that more damping occurred with the copper sheet than the aluminum sheet. This is because the differences in conductivity. Copper has a higher conductivity than aluminum, so by Ohm's law, the current is higher in copper. By Lorentz force law, the higher the current, the higher the force. That is why the copper sheet damped more than the aluminum sheet. As Ohm's law and Lorentz force law predicted, the solid sheets damped more than the cut sheets, and the solid copper sheet damped more than the solid aluminum sheet. While our predicted results were supported, this demonstration did not show the differences in oscillations as clearly as we would have wished. This was because the average magnetic flux density was weak due to the large distance between the magnets. The distance was not able to be shortened because of the methods available to cut the sheet metal conductors. Since the sheets were cut by hand, they were distorted and not perfectly straight. So the distance between the magnets and the sheet metal had to remain relatively large in order to ensure no physical contact between the metal and the magnets occurred. In the future designs, laser cutting the sheet metal would allow us to shorten the distance, which would give us clearer results. Thanks.